to the organisers for inviting me, and it's a pleasure to be here. It's great to see so many people back in person after spending a long time behind our desks doing conferences purely virtually. So having said that, I do have a slight mea culpa in that I gave this the same title and the same abstract in a presentation in a seminar series to IITM some time ago, and only just realized that I doubled up. So the talk I'm going to give now is different from the talk in that seminar series. So if you saw the seminar series, don't worry, I'm going to give you something different. So I'm from University of Western Australia, which is in Western Australia. That's the western part. We just saw that on the climate change maps. And my research is partly funded by CSIRO, which is the Australian Government Research Agency. So there is research that somehow has practical application. And the reason I'm going to mention that up front is that one of the things that we're doing there, which has got nothing to do with this talk, is applying nonlinear time series techniques to geological processes with the aim of trying to identify layer boundaries in geology. And the reason that is important, if I can advance the slide, is that I've got a job going. So I'm looking for a postdoc to do some time series, complex networks. It would be great if you had a background in geology as well, but we don't expect anyone to have all of those skills. Technically, what I'm looking for is someone to do techniques like recurrence quantification. So if that makes sense to you when you're finishing your PhD, go follow that link. You'll find a advert there for a job. I don't think my name's mentioned because it's via CSIRO, but it is, and I'm at the university, but it is working on that. Or email me. The QR code is to the talk that I promised I would give, which I already gave some time ago. So I won't repeat that. But instead, well, I will repeat some of it. I will repeat some of it just because we saw, today's Thursday, right? So we saw on Tuesday, I think Kazu Aihara was talking about embedding and reconstruction and mentioned these theorems from the 80s, both Tarkin's theorem from 81 and the variants, including Sawyer, York, and Castagli's embeddology paper. Now, the whole point of all of these theorems and a lot of my work is, suppose we've got a dynamical system that's too complicated to write down the equations for, or the equations are too hard for me to deal with. Under those circumstances, what can we do if all we can measure is a time series? So the task is to take that time series and somehow reconstruct properties of the dynamical system just from that time series alone. So the theme of this talk will be about different geometric techniques to extract information about the attractor, the dynamical system, from the time series measurements. Okay, so here's my very high-tech, carefully drawn picture. And for the mathematicians in the room, we've got some dynamical system here on the left that's in state space. It's governed by some vector field. We've got some trajectory moving through that. And what we can do is just measure a time series from that. So all we see is a sequence of time points, scalar time points. And the big result of all the embedding theorems is that, well, if I construct a vector just by taking previous time values of that time point, or I'm going forward, but it doesn't matter, successive time values of that point, then that vector is, under some generic conditions, topologically equivalent to the original dynamic of the original system. What that means is that all we really need is a decent choice of time series, and we can reconstruct, this is supposed to depict the attractor, as a sequence of these VIs. Okay, so that's the basic idea. Mathematical theorems, of course, give you guarantees about what's sufficient and necessary. They don't really talk about how things are actually going to work with data. So the theorem basically says this. Take your xt and map it to a vt, a vector, by just taking successive values. And that will work provided m is sufficiently large and provided you've got sufficiently much data. But a better way to do it for real data might be to take some other lag values. Because in general, your time series is going to have a time scale, and if you sample too highly or you sample too lowly, it's not going to be a good choice. And building on that idea, people have said, well, that's too complicated. Let's just take two parameters instead of m of them. So instead of L1 to Lm, let's just take tau and m. So we've got equal spaced. Now it's not going to work. So now we've got space points in the past up to some maximum m. Okay, all good. How do we estimate that tau? And that was the title of the original talk. And really, it's not just about estimating the tau that's here, but it's about estimating suitable choices of previous lags. Right? What is a good way of picking these lags? And so, of course, theorems date from the 80s. There's been a lot of work in the 90s through the beginning of this century where people developed a whole bunch of different techniques to do this. Some of them take the first zero of the autocorrelation, because if you take the first zero of the autocorrelation, your points are somehow linearly uncorrelated. That might be a good choice. Uncorrelated means independent, means lots of information. Of course, I said linearly, so the nonlinear version of that mutual information. First minimum of the mutual information, because your points are again uncorrelated in some sense. Or my favorite, because it's simple, and I like simple things, is figure out what the period is and divide it by 4. There's a whole bunch of other techniques which I won't go through, but I'm going to mention here just because the later slide will be comparing these techniques to the method that I will show you. And essentially, each of these techniques try to find some sort of characteristic length, either by spreading out your points, so that you choose the lag so that in the embedded space your points are spread out as much as possible, or so that in some sense you reduce false neighbors, neighbors that don't obey the dynamics according to some rule. One particular extension of this which I kind of like is, and I will again be comparing to this, which is why there's a picture here, is the idea of continuity. So once you've done the embedding, you've reconstructed the attractor. If you've reconstructed the attractor, the successive points in that reconstruction should be continuous. Right? What's the definition of continuous? Something to do with epsilon and delta, right? So like if you make a small change here, then you've got a small change over there. And we want to add a new lag that gives as much information as possible. So we want to try and break that definition, and this is what this method is doing. The references, by the way, I didn't say at the start, but all of this is in a kind of review paper that we did for Chaos, and all the references are there in detail, and I'll give you the reference at the end of this talk. So there's a host of different methods to estimate these embedding lags, from very simple things, divide the period by 4, through to arguments about trying to disrupt continuity by adding things that are as different as possible. So what do we do? We are going to use some techniques from topological data analysis, and we saw this already. The days are merging together, but it was either earlier today or yesterday. And use those arguments to try to build an attractor, a embedding which has got the right structure. So just a bit about the topological data analysis, and in particular, I'm not going to do as much as we saw earlier. I'm just going to use the basic idea of persistent homology to have a way of counting the holes that you see in the attractor. So what you see here is a set of points, and around each point we draw a ball. and we increase the radius. That's delta. Then if two balls overlap, we say those two things are connected. Right, so here on the left, we've got nothing connected at all, everything's disconnected. Here we've got 1, 2, 3, 4, 5, 6 discrete dots and one thing connected. If you're really sharp, you would have noticed that I had 8 bits here, and this thing B0 is 8. Here I've got 7 clumps, and B0 is 7. Here everything's connected together in one clump. B0 is 1. But without going into the details, I've got a hole in the middle. That's what B1 is measuring here. If I keep making the circles bigger, the radius is bigger, eventually the hole disappears and everything's fully connected. We've got a fully connected graph. So the property that I care about is the persistence of the Betty1 holes, the persistence of these holes. For what range of delta values do I see a hole exist in the data and stay there in the data? Right? So that's what I'm going to call persistence. So what we do is we start by getting, I'd like to pretend that this method starts from 0 and then estimates all the numbers that we need, but it starts by estimating a characteristic time, which is something like the period of your data. Because what we're going to try and do is take the long data set and chop it up into short chunks and kind of in a very hand-wavy way, if you think about a nonlinear attractor, it goes around in circles, right? And we want to look at each of those circles individually and see to what extent the embedding creates circles that are full. That makes sense. And that's what this is doing. So I just determine my period, or quarter of the period, construct a 2D embedding with that, 2D embedding with that lag, and I take strands of successive points in VT. I'll show you a picture in a moment, that correspond to individual orbits of that attractor. Apply that idea to each of them and see to what extent those short strands of data create a persistent hole. In other words, to what extent is each of those short chains an orbit, in a very geometric sense of orbit. And I then, for each of those individual strands, compute how long it stays as an orbit, and then compute the average of that, and that's my persistence. It's a number. It's a measure of how much that particular choice of embedding parameter has generated things that loop around in circles. So here's the picture. Again, high-tech animation. Here's my time series. So I found it was annoying when someone pointed at the edge screen or pointed at the middle one. Here's my time series. And I chop it up into these chunks that are just basically roughly an orbit each. Right? So this first chunk here might be those points. This chunk here might be these points, and so on. And for each of those chunks, I then take those few data points, grow balls around them, and see for how long I get a persistent hole. This one, maybe it doesn't happen at all. This one's a little bit. This one's bigger, because that's bigger. And that measures now how each of those strands are filling up my embedding space. Okay, so that's persistence. I then want to invent a couple of other measures that also will help me out here. One is, well, to what extent are these things circles as opposed to ellipses? Because if I'm dealing with data, circles are good, ellipses are bad. Why are ellipses bad? Well, ellipses are bad because they squeeze the data together more. I'd much rather have things spread out, just from a purely data-driven approach. And I'd certainly want to have it look not as messy as possible, and I'd certainly want to avoid daggy tails. Right? So I want to have these orbits being all circular and nice. And so I've got two measures of this, one which I'm going to call circularity and one which I'm going to call efficiency. Circularity is just, I take each of those strands again, find that lump that is a solid in there, and then just look at the principal eigenvalues of that to compute to what extent the expanse in those two directions is equivalent. Right, so the ratio of those two principal eigenvalues gives me the roundness of that data set, that strand of data. Second one, efficiency. I want most of my data to be used up to draw my hole. I don't like these daggy bits on the end. And so I compute the size of the hole according to the homology definition that I showed you earlier. And I compute the smallest convex polygon over the data. Right? So the smallest area that the data can be covered by. And I want that ratio to be as close to 1 as possible. Okay. So in summary, circularity, efficiency, take those two things, multiply them together, that gives me significance, what I call significance, and I've also got this persistence idea sitting behind the two of them. So just very quickly, I want to show you the application of this to some experimental data. So this is a experimental data set. So the paper's got lots of other data. It's got all the standard test cases, Lorenz, et cetera, et cetera, et cetera. This data is more interesting. This is a lobster neuron spiking. This is data that was collected by the group of Henry Abarbanel at UCSD. Henry very recently passed away, I've just learned. But this data is really interesting because it's got lots of different timescales. Anyone that's worked with neuron data or ECG data and tried to do embedding, you will know that it's very difficult to capture the dynamics at the different timescales all at the same time. Right, so the traditional methods tend to fail in producing good embeddings of this. And I'm just, for the sake of this talk, there's details in the paper, I'm just going to show you an example of, this is the continuity approach of Pecora. This is another approach of one of the geometric methods that I flipped through earlier. And this is the approach of what we're using here with these lags. And what I'm showing you is the three-dimensional embedding here and two-dimensional projections of that three-dimensional embedding. So why am I happy about the third method doing something different and something apparently a little bit weird? This one here. What's good about that? Well, what's good about that is that it's identified that there's a fast time scale as well as the slower time scales. And it's taken, if you think about it, taken the embedded space, squished it down, and focused on that part there. Right, so the structure flipping up and down is now nice and neatly embedded here. Right, so the method's got the ability to select these different lags that capture different parts of the geometry. I'm only showing you one example to hopefully, for those of you in the business, to whet your appetite enough to have a look at the paper. And if we try prediction on this, that's the original time series. That's our new method, and these are the other two methods. The prediction algorithm doesn't matter very much, but it's the same for all of them. And simply put, none of these are very good. They don't look at like this exactly. This is a free run prediction. But at least it's got, sorry, it's not a free run prediction. It's a fixed time step, but far ahead prediction. Right, so I project 20 steps ahead, then move forward one, project 20 steps ahead again. Right, so that's why you see the amplitude is decaying somewhat. But the dynamics here is much more like this, I claim, than these other ones. So it seems to be kind of doing something right. We can do the calculation, and I'm showing the results here for both the standard Lorenz test and the lobster neuron data that I just showed you. And what I'm doing is the comparison of the model prediction error of the two methods. And what you see is that the topological method, this one here, has lower mean, lower variance. Okay, it's got some massive outliers here in the lobsters, so when it gets it wrong, it gets it really wrong. But so do the other ones. So it might be a nice way of choosing different embedding lags, and the method is entirely based on the idea of looking at the geometry of your time series and the geometry of your embedding and how that geometry produces a nice shape. And that is the second part of the talk, which is a separate piece of work where we're also looking at methods to construct properties of the underlying dynamical system by looking at the geometry of the time series or the embedded time series. Or in this case, we're not actually embedding it at all. And so for those of you that saw the other talk, this is the new bit. So what we're going to do is build a method to construct Poincare sections, first return maps, from data in a generic way. So everyone knows how to compute first return maps, right? If you've got a time series, everyone's read Lorenz's paper about the famous Lorenz equations, and in that paper he infers a first return map, which basically is a nice pointy one-hop map, like that, and he does that just by looking at the peaks of the time series. That's good, amazing paper. If you haven't read it, go and read it. It's an amazing piece of work, but it only works sometimes. It works when it works. So what we're trying to seek is a way that's going to work robustly, a way that's going to suggest good choices of first return map and Poincare sections, irrespective of the time series that we start with, to at least a greater extent. So we start with our time series. And by the way, the other approach to getting Poincare sections is you do the embedding, you then construct a plane perpendicular to your flow, and then look at intersections of that, and that's computationally a mess. I mean, it's doable, but there's a lot of stuff happening there. We take our time series, and with each point in the time series, we identify a window. So just look at the last one here. So I've identified with this point in the time series a window consisting of 1, 2, 3, 4 points. And what I'm encoding is the shape of those 4 points. Right, so this is the ordinal sequence idea. Those 4 points, well, those 3 points are the ones I'm using for this. That one is a green one, it's for there. Right? So I've got 3 points in the blue section, 3 points in the green section. Just looking at the 3 blue points, well, this is the second smallest, this is the first smallest, this is the third smallest. 2, 1, 3. Right, so for each of those windows, I get a code word which encodes the shape of those sequence of points. So I then take those different code words and I look at them on the attractor. Well, I don't actually need to go to the attractor to do this, but going to the attractor is really illustrative here. On the left is the standard way you might think about a Poincare section. This is, in fact, the Poincare section that Lorenz got with his peak of the Z value of the time series. But if we take each of those code words with a different color here, you can see that each of those code words corresponds to distinct regions of the embedded signal. Right, so in other words, I see 2, 1, 3 in a clump. I see 1, 3, 2s in a clump, and so on and so on. And the most intuitive way of thinking about it is these dark green ones here, those are the ones where it's always going up. So that's 3, 2, 1. These are the ones where it's always going down. That's 1, 2, 3. And these are the various other things that might be interesting. We then look at successive first entries into each of those regions, and that defines our Poincare section. So the Poincare section is simply these darkest points here for each of those things. So we've naturally, without trying to construct hyperplanes, got a way of building effectively a hypersurface that is perpendicular to the flow, and I can look at successive points on that, in that series to give me the first return map. And the surprising thing for us is that sometimes reviewers give you really good suggestions. We originally submitted this paper to Chaos, and one of the reviewers came back and said, yeah, it's good, but how robust to noise is it? And I thought, oh, probably not actually, because there's lots of stuff going on here. It could get complicated. do the calculation anyway. On the top, I'm showing you signal-to-noise ratios going from 100 dB, so very little noise, to 30 dB, using Lorenz's original approach, first maximum. And that's our method, just picking one of those sections with the same noise level for the same time series. So by eye, to me, this one looks about as good as this one. This one, it's a bit worse than that one, but certainly better than that one, and so on. So there's a robustness to noise built into this. And I will finish there because I know that everyone's waiting for the conference dinner, and there's still one more talk to go. And I'd love to get some questions from you. Just full credit where it's due. The embedding stuff is in a paper by Eugene Tan, who's one of my PhD students and my co-authors. That's the paper that covers the stops, delay embedding stuff. And Zara, who's another PhD student, wrote this paper. That's the Poincaré section stuff. So I will finish by acknowledging all those people that did the work. I don't quite have 5 continents. I've got 4 continents, but I did count there's 7 countries there, so I reckon that's pretty good. Eugene and Zara, the PhD students, Deborah, Dave, and Thomas are colleagues of mine and co-supervisors of the students. If you've got questions later on about this, please email me. If you've got questions about the job I mentioned earlier, please email me. Perth is a fabulous place to live. It's a long way from Sydney and Melbourne, but that's both good and bad. And we've got the best cricket team in the domestic T20 competition. Not quite up to Indian standards, but any questions? Yeah.
When you use this style for determining tau, what about determining the dimension? How do you choose the embedding dimension? You can do it by the usual methods independently, or you have something related to this way of doing?
Good question. So for all intents and purposes, as far as what I've presented there is concerned, we just do it with the usual method, so looking for false nearest neighbours and so forth.
False nearest neighbours, okay.
But there is actually a bit more to it than that. Mm-hmm. Because you're choosing a non-uniform embedding, what you can do is compute a measure of how much more information you get out with each increase. Mm-hmm. And so sometimes the optimal embedding dimension is a bit different if you use that measure. So sort of an information gained by adding more lags.
And also, roughly what is the estimate of the size of the data required for a sincere embedding?
For the first part? Or the?
Yeah.
So for the delay estimation stuff?
Yes.
So it's not bad. I mean, it's not as good as autocorrelation. I mean, like all of these methods, you need to have several orbits to identify things, and that's kind of where you're stuck. As long as you've got enough orbits, then you're okay. Where this method has benefit is that topological data analysis and persistent homology are notoriously computationally inefficient techniques. But we're not doing that on the entire data set. We're doing it repeatedly on short segments. So we can gain a fairly efficient algorithm to compute those interesting properties over the short segments. And so in a sense, getting as much information as possible from each orbit. In terms of the data requirements, it's comparable to what you get out of mutual information, autocorrelation. Probably better than mutual information. The examples that we have in the paper, we gave examples at a level where mutual information was breaking down and saying silly things. But our method wasn't.
Other questions? There's one.
Yeah, hi. Thank you. That was a really good talk. I wanted to know how you, after getting the lag, how you then actually forecasted the time series, because what you get with Tarkin's theorem is the diffeomorphic attractor, but you showed that you were able to get the actual series, like you predicted the lobster series. So how did you do that?
So the prediction part was essentially just a way of testing how good the embedding was. So having got an embedding, if we use that chosen embedding lags as the input to a machine learning algorithm, which one gives the best performance. We were using a variation of reservoir computing for that, but it doesn't matter terribly much. We were just using the same machine learning algorithm for each of them to get a measure of performance. Obviously, different algorithms give you different results, and you could go, entire conferences are devoted to that one thing, right? So we just chose one method that was, we felt, defensible and simple and worked well across all the methods.
Okay, thank you.
Yeah, it was a pleasure to see your serious advances in improving the embedding techniques, and hopefully we'll avoid many artificial results in the future.
Well, I think, I'll take that as a question, if I may.
It was a compliment, was not
I
a question.
know it was a compliment, but like all of these methods, there's some art as well as some science, and people can get crazy results if they do silly things with it.
Yes.
And I don't think this solves that problem.
Yeah.
My advice is only make the algorithms so complicated that you idiot-proof them in the way that the people using them have to understand them before they can use them. But, yeah.
Okay.
Okay,
Yeah,
thank you.
well, thank you very much. Applause.